Good morning, everyone, and welcome to session S12, Stability of Tubular Sections. My name is Ali Muravet, and I will be moderating this session today. We have two great presentations. Before I forget, we have the PDH code there for those who care about that PDH code, and we will repeat that PDH code throughout the presentations. So we have the next presenter. Dr. Abelter Leon from Virginia Tech. He's going to talk to us about concrete fill composite tube columns.
Thank you, Ali. Good morning, ladies and gentlemen. I'm presenting this talk on behalf of my former student, Tiziano Perea. So I'm doing it on his behalf, and I hope to be able to do a good job for him. We're going to go through the motivation for this study, some background information, and then probably spend most of the time talking about two different approaches that we're contrasting in this study as to how to determine buckling loads for experimental cases where you, in fact, could not reach the buckling load in the specimen because you run out of capacity in the testing machine or in the testing setup. And that's, in our particular case, as we're going to see, is because we're using fairly large specimens. And so we're going to make some comparisons between analysis and experimental results and offer at the end some final remarks. This was a study that we did several years ago. It consisted of testing very slender concrete filled tubes. There were actually 18 specimens, and they ranged from about 5.5 to almost 8 meters in length. We had both circular tubes and rectangular tubes. And this work was conducted at the University of Minnesota at the so-called MAST lab as part of a NASCC project funded by NSF. But the overall, or the overarching objective of this study was to look at fairly slender concrete filled tube sections. And if you pay attention here, perhaps it's not clear to those in the back, there's Mr. Perea, and this is the column. So these are pretty, again, almost some of them almost 8 meters long. And so even though some of the tubes are in the 20-inch range, they appear quite slender in this. What we were trying to do was to obtain data to calibrate the provisions in the AISC specification for composite columns. When I initially proposed those provisions and appear in the 2005 version of the spec, there were lots of gaps, particularly for very slender sections. And so we conducted this experimental campaign in order to kind of fill out the data set with slender elements. And we run a very complex set of tests for each specimen. And we first started with case one, which is a concentric load case, or the Euler buckling, if you want to think about it this way. The second one was a uniaxial cyclic test. A third was a biaxial test, and we finally did some torsion on these specimens. And if I can get this started, not sure if that's running, yes. So here's one of our specimens, and you're going to start seeing things displacing quite a bit. By the way, those yellow frames that are hanging there are also for the digital correlation measurements. And so we have spectacular set of data on these column tests. These are probably, I'm quite certain that I can say these are the best documented column tests ever. And if you're ever interested, that data, by the way, is sitting out there in a public repository, so you can use it. All right, and so what we were trying to do, again, is verify our design provisions. So we started by looking at our usual interaction diagram and doing basically, again, a buckling test, which is shown there by that red curve. Again, because of initial imperfections and other things, of course, you never go straight up the vertical axis, but you do get very close to the actual buckling load up there. And so that was the first test, and that was to basically try to tease out all the stability effects. We then did a number of combinations of axial load and unidirectional lateral loads to look at different points along the interaction diagram. We did that initially in one direction, and then we did bidirectional, right? And because we had the best toy in the industry, then we went ahead and did crazy things like this, which actually are very good tests of whether your analysis can track things. This is a very complicated load history and sudden changes in direction and so on. And again, the last thing we did was to actually do torsion on these specimens, and these are actually the only, as far as I know, the only well-documented torsional tests on any kind of concrete filled tube section. And we did this for all of our specimens whenever possible. But as I mentioned before, and I called it a toy, this 6 degree of freedom testing machine is actually quite amazing. And so I'm going to show you here very quickly the plots at the very top of what is the ratio of the load versus the maximum load, and the axial displacement versus the maximum axial displacement. And these are in percentages. In the second line here is the displacements in the x and y. So the z is the axial direction, the x and y's are the lateral directions. And at the very bottom are the forces in that in the x and y direction. And the reason I'm showing you that is because, in fact, this testing machine was simulating a fixed base condition and a pinned end condition at the top. And so ideally, these forces down here should have been 0. They are not, but they're very small. These are in kips, and so we might have been getting half to 1 kip of lateral force, while we were imposing perhaps 1,000 kips of vertical force. So it's small, but I wanted to bring this to the fore because when we did the analysis, and my analytical comparisons are actually run to the actual load histories that we derive from the tests. So we actually took these displacements and load histories and input them into our models. They are not idealized load histories in the studies that we did. And so here is our typical test. And so in the case of a very slender column, right, we have fixed base, and pinned at the top. So ideally, we have something like a k equals to 2. So in fact, when I was telling you that I had a column that was 8 meters long, the effective length was actually 16 meters. So this is pretty slender. Okay. And for most cases, we were able to buckle the columns. On the left-hand side, you have the column in its initial undeformed position. And on the right-hand side, you have the column buckled and appreciably buckled. Okay, and we were able to obtain this kind of buckling for most of our specimens. And we documented these tests very well, including, for example, great information from the digital image correlation on the actual deformed shape of these specimens. You would think that the eccentricities would be very small, but in fact, if you have something that's 26 feet or 8 meters high, and you are trying to put it on a fixed base, you can never weld it perfectly, and the tube itself is not perfect. So all of these imperfections were also put into the analysis. The only thing we couldn't really put into the analysis were the residual stresses, or I should say the actual residual stresses. We actually tried to put some residual stresses, that come from the literature, but we didn't have the actual residual stresses in our analysis. But the trouble that we run into, and it was not something that we were not prepared for, was that we wanted to test things that were fairly big. And so 4 of our specimens, okay, the HSS round tube, 20 inches by 1/4 inch, and the HSS 20 by 12 by 5/16. Both of those would give us buckling loads that were much larger than what our machine capacity was. Okay, and so what we observed was that in some of these cases, right, we could not get to the actual buckling load. And let me explain this diagram just a little bit. This is again, an axial load moment diagram. Shown by the dashed gray line here is the cross-section strength, okay? Shown in the dashed black line is the interaction equation that we have proposed for design in AISC, okay? Shown in red is the theoretical buckling load, and the blue lines are our tests. And you can see that in some cases we run the tests up and down a few times to do that. But in both of these cases, in the case of this particular section, we didn't quite get up there, although it's kind of getting there. This one certainly, the other one over here, certainly did not come close to the buckling load. Oops. And similarly, again, for some other of the specimens, and we were a little concerned about this because if you look at these 2 specimens, you will notice that there is, in the one on the left-hand side, which is the one, unfortunately it's not showing up except at the bottom here, these are nominally the same specimen, okay? These are the 20 by 12 by 5/16, but this one here is with 5 KSI concrete, and this is with 12 KSI concrete. And you can see that there's an appreciable difference in the drop that you get between the 2 concrete strengths, okay? And so we were interested in trying to figure out if all of these things that we could, or that we predict analytically, actually happen. But we could not reach the actual buckling capacity. So Tiziano decided that he wanted to look into a way of perhaps taking the kind of result that we had and extrapolate. And those of you who were in the audience for Professor Ura's presentation remember this name, Artin and Perry, and the date of 1886. And in fact, the methodology that I'm going to show you here, or one of the 2 methodologies that I'm going to contrast, actually comes directly out of that. Is directly out of the equation that Dr. Ura showed the other day. The method 2 is exactly the same one, but it was derived independently by Southwell, and it's well known nowadays as the Southwell plot. That was in the mid-30s. And Southwell derived it completely independently. He apparently didn't know anything about the Ayrton-Perry formula. And he was recast by Donnell in 1938, okay? And basically, these methods are based on looking at the deflected shape of the curve and looking at it as a series expansion and chopping everything except the first term. And if you are in the elastic range, okay, and you look, for example, the original Ayrton-Perry formula is shown here, the Southwell is here, and the Donnell is here. All of these, okay, give you a straight line, and depending on what you're looking for, right? For example, in the Ayrton-Perry formulation, this distance along the abscissa is the inverse of the buckling load, okay? Here, it's buckling load itself dividing a constant, which is the slope, and the O'Donnell formula is basically the inverse of the Southwell plot. But if you look at these, they're basically the same thing, okay? And what you do is, if you, for example, had a couple of points or several points along the loading, you can take those, linearize, and extrapolate to what the buckling load would be, which is what we are doing. Okay? And so we don't have to get to the buckling load. We can extrapolate, or at least we think we can. I must say, again, unfortunately, there are things that are not on the screen here. Very important. This, of course, holds only, strictly speaking, in the elastic range. And because some of our columns were actually going into the inelastic range, and we would expect them to do that as the slenderness decreases, then these formulas are not, strictly speaking, applicable to some of our cases. But they work very well, as shown in these original plots from a study by Horton in the 1970s on small aluminum columns. You can really get a great fit to the data from following that. Okay, and so we looked at this, and we tried to apply it to our load cases, and they didn't work very well. And so what Mr. Perea did is, rather than looking at the secant, because that's really what all of these formulas are doing, they're looking at the change in load versus the change in deflection, which means you're looking at the slope or the secant line. He decided to try to look at what happens to the tangents. And so basically, these two things are contrasted here, and they give you different results, okay? Because the O'Donnell or Southwell plots are basically going to give you the Euler buckling load, okay? While if you look at the tangent approach, you will get the actual buckling load, okay? And so let me walk you through here, through one example of what happens to one of these columns as you go to different slenderness. And again, I apologize, the things that appear on my screen are not there. Basically, this is the same column, okay? This is with a lambda of 0.5. This is with a lambda of 0.97, okay? And quite arbitrarily, we agreed that we were going to look at points at equivalent to 0.8 and 0.6 of the ultimate load, pick those 2 points and linearize, okay? So the blue line here is the analytical result with everything built in, and the red line here shows the linearization that we proposed. You will notice, and we've figured this out quickly enough, that as you went, again, from a relatively short column here with a lambda of 0.5 to 1 and so on, and here are the ones for 1.41 on the left-hand side and 2.98 on the right-hand side. And you can see that as we get progressively more slender, these formulas begin to give very, very good results. Okay? And this is the approximation proposed by Dr. Perea. We looked at changing a number of parameters, and so here are a number of curves that look at different initial imperfections. So the top one is L over 1,000, L over 500, L over 250. Okay, and you begin to see here that there's certainly an effect of that initial imperfection, but it's not huge. Technically, right, we will probably, if we were just looking at purely the buckling load, there wouldn't be any difference. But this approach does tease out some of those subtleties. Okay, again, here are some comparisons between the tangent approach, which is shown here, and the secant approach, right? Both of these, interestingly, of course, can be plotted in the same diagram because they are slopes. So you can do that without any problem. And you can see here that in our case, we are doing quite well, right, at a 136 versus a computed one of 129, while the secant or the Southwell plot would have predicted a much larger value. And similarly here, we did any number of studies along those lines to convince ourselves that this worked. Again, I'm not going to spend a lot of time. This is a similar plot here. And of particular interest to us, this seemed to work better as we got to more slender but larger sections. And so that's what we wanted to do. What I just showed you before were all analytical studies. Here are similar plots, but these are exclusively from the test data. And you can see that we are doing rather well, okay? Typically, when you start a test, there's a lot of noise down here. So, you know, you really need to pick a couple of points. And I said, again, we picked 60 and 80% of the ultimate value sort of arbitrarily because most of those points tended to fall in a fairly linear range of these plots. And so as you climb over above about half of the ultimate capacity, this thing becomes pretty linear. And so this allows us to basically go back and recalculate all of these capacities, okay, or I shouldn't say calculate, extrapolate those capacities. And so this is what we got. And just to compare, the two important numbers are basically this column here, which compares the secant value versus the nominal value, and this is the tangent value versus that. And you can see that the secant value, not bad for one of the specimens, but for the other ones is way off. And here we are doing quite a bit better, even though it's not perfect. And so we are careful or need to be careful in just saying that this is an approximation, but it is something that is actually quite valuable to us because we were then able to, of course, come back and plot all the results from the 18 tests into the column curve and get what I think is a pretty good match. Okay? And so that gave us a lot of confidence that the design provisions that we have in the AISC specification are correct. And so with that, just some concluding remarks again. We contrasted a secant versus a tangent approach. And this was done because we had incomplete data and wanted to try as much as possible to extrapolate and get some reasonable approximations to true values of buckling. Okay. And we looked at different ranges of lambda and different ranges of initial imperfections. And we found out that insofar as the lambdas are concerned, the larger the lambda, probably the better the technique works. It works equally well for different initial imperfections. So whether you choose an L over 500 or an L over 1,000 really doesn't matter very much. And with that, I'll thank you for your attention, and we will be glad to take some questions.